So, okay. So I'll be talking the content in three different perspectives, starting from the basic introduction of Raman spectroscopy, which covers the Raman effect, characteristics of Raman bands or scattering process, and why the Raman spectroscopy is important, and the key difference between IR, that is infrared spectroscopy, and Raman spectroscopy. And I'll be touching upon some the basic concepts of molecular vibrations. And the second part will be the instrumentation. I'll be covering the instrumentation side. So what are the components in the spectrometer, and what are the handling procedure, and few things about getting a good quality spectrum. For that, what are the parameters are influencing to get the spectra like that. And finally, the most important thing, the spectral interpretation. So how the bonds, especially how the molecule can be predicted, or understanding the structure based on the bands, I mean Raman bands. So I'll be discussing about. And finally, I'll be covering the applications part. So how this tool can be helpful in various domain. So like that way I will be discussing. So Raman effect or Raman spectra is based on the Raman effect. As we all know that the discovery was made by our own scientist, Sir C.V. Raman sir, in the year of 1930. So he have established this concept based on the inelastic scattering of light. So when the light or electromagnetic radiation is if interacting with any material, it gets scattered. So that scattering will be a change in the wavelength. So the light coming with a particular wavelength or energy, after the interaction, it gets scattered. So that scattered light have a difference in the incident wavelength. So that's the key here. So the change in the wavelength occurs when the light beam or electromagnetic radiation by a molecule is all about the Raman effect. So let me make it little clear. So as you can see here, so what happens exactly? So we have a light source or a single electromagnetic radiation falls under any material. It undergoes different process, and not only the scattering process, it may undergo emission, or completely, if it is transparent, that will be completely transmitted, or some of the photons or the light energy will be absorbed within the material, and also few portion of a light can be scattered. So all can happen together. So Raman, Sir C.V. Raman sir was highly interested in the scattering phenomena. So the whole idea is all about or deals with the scattering alone. We are not interested in the other process like transmission, reflectance, and absorption, because he thought that the scattered beam or scattered light have information about the structure or molecular environment. So that have a fingerprint identity, so that in such a way that the materials are scattering the incident light. So we can understand that when the light enters in the molecule or start interacting with the material, the electron density within the atoms and molecule are responsible for making this kind of frequency shift or wavelength. That shift are considered to be a fingerprint information of a particular material or a structure. So are interested in the scattering phenomena, the scattered light can be further classified into two different process. Like if the scattered light have higher or lower wavelength than the incident light. Say for example, if the scattered light have a lower wavelength, then it can be named as a Stokes lines. Or in the opposite side, it may absorb or gain some energy from the photons, and the scattered light may have a higher wavelength than the incident one. That lines are anti-Stokes lines. These two lines are basically Raman lines, Stokes and anti-Stokes lines, and there can be a lot of possibilities. There should not be any change. So it simply comes and interacts, then it goes. So there will not be any significant change. That kind of scattering is called as Rayleigh scattering. There is no use for that. We will not get any information from the Rayleigh scattered beam. Like the situation can be, you can understand, like you are listening this talk, end of the 1 hour, maybe I hope few will be understanding a little bit from the Raman spectroscopy. You all Stokes lines. So you get something after this session. The same way, light coming and interacting with material and coming out with some inelastic process, like the scattering is have some change in the wavelength when compared to the incident light. Okay, so that is helpful. So So we'll be getting the information from the Raman lines, that means Stokes or anti-Stokes lines. So what are the characteristics of the Raman spectrum, how we are getting the data? So as we can see, we'll be plotting the wavelength or Raman shift. Why we are saying it's a Raman shift? Because it's coming with a particular frequency because of the molecular structure or the vibration level. So it undergoes the shift process, the wavelength getting shifted. So that shift is very key here. So we are getting that information in terms of wavelength in numbers. We are plotting against the intensity. So this is a typical denotion of Raman spectrum. We have a wavelength with a particular frequency versus the intensity. Basically talking, this process is very, very weak process. Why I'm saying weak? Because as I told you, only few portion of the photon only can be scattered. Even that, only very less amount of photon only can be expected as a inelastic scattering, like Raman lines, either anti-Stokes lines or Stokes lines. Maybe most of the light can be elastically scattering, so there will not be any much information as there is no change in the wavelength. So like other things also happening, no? So we are getting a very weak information, but the detector, all the optical compounds do the job to get their information the quality manner. So we should understand that the scattering is very, very weak and very sensitive. So say, for example, hardly 10 to the power of 4 photons, we expect at least one photon can be a inelastically scattered photons. Okay. And so that in few compounds are very good, good choice of doing Raman. That should have a very good electron clouds, because the electron clouds are mainly responsible for scattering the electromagnetic light. So the pi bond structure conjugation kind of bonding is very helpful to get a good identification of a material. And why we have Raman spectroscopy, why we are very interested to do Raman or know about things, is very simple, because we easily get the information about the vibration levels, which kind of vibration it is either symmetric stretching or anti-symmetric or rotational, what kind of vibration level a material have. These kind of things we can easily get it. And of course, it's a complementary information or technique to the IR spectroscopy. Maybe in the next slides, I'll be talking about some key difference between IR and Raman. Of course, this technique is completely a structural information. So what is a phase? What is a functional group? What kind of molecular environment within the molecule? These things we can get directly. So of course, maybe IR and X-ray also serve the same purpose, but not exactly. So we'll get some additional or complementary information similar to the IR and X-ray diffraction technique. And it is mostly helpful for understanding the homonuclear molecules like because it has a lot strong electron clouds, so that cannot be easily understood by conventional technique like other microscopy or other characterizing tool. In that case, Raman is highly helpful to understand the homoatomic structures. And the in situ analysis is highly useful for organic and inorganic. So you can easily do by Raman. And the analysis of aqueous solution-based compounds or solids can be any form, is easily we can acquire the spectrum. So these are the key advantage. And the sensitivity or detection limit is quite high. If someone plays with the key parameters with the laser, so you will be able to precisely identify the impurities. Very small amount of impurity, even some small amount of dopant effects can be easily predicted by the Raman shift value. So that way it is superior to other technique. And here we should know why still we have a Raman when we have IR. So why we have the technique. So there are a lot of similarities, but I'll directly insist about what is a key criterion between IR and Raman. For doing Raman, that sample need to have a very high polarizable nature. That means change in the polarizability, it's a key factor. That means it should have a permanently polarizing capability. That means the negotiation of the electron cloud between any two atoms should be more preferable. So that kind of samples will give a best result or easy prediction of a structure. In the case of IR, maybe the polarizability also works according to some rules that like mutual exclusion principles. But if you look for a IR, that compound or a structure should have a dipole effect. So dipole is a permanent charge species located on two different atoms. So it's quite different with the, polarizable phenomena. So if you feel that molecule is highly dipole compound, then you can go for a IR instead of Raman. But if the material suffer by symmetry elements, that means atoms or molecules arranged in the space, though they have a strong dipole, it suffers by a symmetry like center of symmetry, inversion symmetry effects, then you may not get a exact band from IR, because IR is a only single wavelength. That's only like IR wavelength energy only it absorbs from the vibration level. So it fails to give the exact structure by using IR. So in order to address that kind of issue, that means materials suffer by strong symmetry elements, then you can switch to Raman. Raman is highly helpful to understand the structure, though they have a complex symmetry. Okay, and other things, maybe the solvent usage and the sample preparation for IR is a bit complex. You need to have a proper standard. That kind of issues are there. In that way, Raman is very simple. You need not to have any special sample preparation, or literally no sample preparation is needed for doing Raman. And of course, it's quite precise information and quick technique to get the structure. And maybe Raman is highly expensive when compared to IR, but the collection of information is completely different from IR. Though the frequency number or everything is saved because it's origin from vibrational spectroscopy, but still you will get a lot of information from Raman. So let me understand better what the polarizability and dipole effect. So as we can see here, so if any heteroatoms, like it is highly possible with the two different groups or atoms bonded together, so they have a negotiation of the bonding. So they have shared, if you assume that mutual bonding, covalent bonding, still the electronegativity change within the atoms, they try to pull their electron towards one atom's towards their side. So the electron clouds are not stable within the structure, so it keep on oscillating with the entire either side or that side, like. So this have a positive effect in scattering the light. So this called the polarizability. So this polarizable nature is highly helpful in scattering the photons or electromagnetic radiation, so that though the material have the irrespective of the symmetry, so we will be able to get the scattering can be possible. But if the dipole moment is like a same phenomena, but the separation or the equivalent splitation of the electrons or the bond can be easily split into two different heads. So that can be partially plus and minus. That will be permanent, relatively stable charge species sitting onto the head. So this is a dipole. So they will act as a perfect dipole because you can exactly denote plus and minus within two atoms. So that kind of dipoles are highly sensitive, or it has a capability of absorbing the IR radiation. So if you do IR for dipole compounds, that will be easy to get the structures. So this is a key difference between the polarizability and change in the dipole moment during the vibration, because the atoms and molecules are keep on vibrating within the structure. So that makes these kind of effects. Okay, so these are the typical examples. What are the structures, or what are the stretching is possible, and what kind of molecule you can think about Raman or IR. And these are just a notation of different vibration structures. So it's like atoms are hang out within the string notation. So it keep on. It's not a stable or stick bond. So it keep oscillating within the molecule. So this is useful for shifting the electron clouds, or maybe for creating a dipole within the atoms. So again, from that, basically the point loop symmetry. So this is a idea or some calculation based on the symmetry. So as the molecule keep on vibrating within the molecule, so it has a spatial deformation in the axis, in the particular axis. So scientists have predicted what kind of symmetry as like XRD. So what are the possible HKL indexes are possible with the structure. The same way, people also had a calculation that one particular molecule, what are the ways of rotating based on the center of the axis. So they give the notation and create the symmetry elements. So these elements are representation of what are the possible stretchings and deformation within the molecule. So mostly you would have seen in Raman spectra, the bands are denoted by some symmetry element like E2G, F2G, A2B. Like these are the combination of the rotation or the vibrational rotation in space it's addressing. So in that vibration is only respective with the particular wavelength. So if it matches, then definitely you will get the band. So we are just matching with the structure and with respect to the wavelength number. And this is special, I mean, some focused stretching a diagram of the oxide system. Mostly some oxides and complex oxide, they have a F2G band. They highly sensitive with the Raman scattering. So what are the possible stretching I have given, like in axis and anti-stretching, like it is completely rotating towards the axis, and in plane axis also will be there. So the bending also possible. What you see, the black no head or the oxygen atoms or the central cation is still playing with their interaction, so it keep on rotating within their axis. So these all collectively give a symmetry element like F2G, kind of we can assign from the point group theory. Then we'll, if you get the Raman data, you can simply name it what position it is, you can tag it. Okay. The basic components of the spectrometer, we can classify under 4 categories. The first and foremost thing is laser, because we need an excitation source. It's nothing but light, but it's not a normal white light. We should use a single wavelength. Then only we'll be able to predict this particular light with the energy is shifted in this much, like that. Okay, so that's excitation source is required. And the spectrometer, of course, it's all optical components and gratings and filters to route the source, I mean the light, because it's acting like a traffic signal. It is directing the light to the sample. So the main role of the spectrometer is align the beam, especially the size and the width, and a lot of filters will be there. So and associated rays also will be there. So that all the things can be taken care by the spectrometer. And we have a microscope. This microscope is absolutely a complementary one. You can also, so most of the people are aware about FT Raman. FT Raman does not have any microscope facility. So simply you can place a sample, but you may not be able to see the surface. Okay, you generate the light and allow to shine on the surface, you get the spectra. But if you have a microscope also allow the light to fall under the sample, but you will be able to see the sample. You can see the surface where you are interested. If you want to see or know what it is, you can exactly allow the light onto the head and to differentiate what is a two particle it is, if it is there or not, like that. So that way microscope is helpful. Maybe in the future slide I'll be telling the most applicability about the microscope. So it serves two purposes. One is, again, the light is falling through the microscope, you can view the sample, and same, the scattered light is collecting back through the microscope and directing to the detector. So the fourth component is a detector. It's again a most crucial component in the device, because that only getting the information. What is the change in the wavelength? So light has come, and after the interaction, it got inelastically scattered. And what is the change in the wavelength? So detector will tell you that particular information. As it is very weak, so the detector should be very, very, very precise and sensitive. So basically, it's made up of photo diodes array, or kind of CCD kind of things. So all the electronic components are highly sensitive to capture the information. What we have at our institute. So the Raman microscope, microscope from United Kingdom. So as we can see the numbers, the one is a source here. Hello. Yeah. These are the source. We have a two laser source here. So one is 532 nanometer and 785 nanometer, and it produces a monochromatic light and falling, passing through the spectrometer and reaching to the microscope. The third component is a microscope, and here we can place a sample simply by pressing the surface should be flat. That's it. Then you can view the sample, and wherever you're interested, you can focus on that. You allow the beam and get the spectra. And the fourth component is the detector here. So laser 1, 2 is a spectrometer, third one is a microscope, and finally the detector. And popularly, we have the 532 nanometer, I would say, of lasers like cover wide range of material. Like 532 or 480 is somewhat okay. So you can get most of the, you can do most of the sample, especially useful for semiconductors. And the usage of 785 or even higher, 1064 nanometer is people are preferred because of the effect called fluorescence. So if you have a substance or a material or a powder that have a functionality or a structure have a strong fluorescence effect. That means when the photon is interacting with the material, it may undergo the emission process because already the functional group absorbs some portion of a light, and later it's slowly releasing a secondary emissions starting from the functional group. So that creates a background. Okay, as I insisted, this entire process is a very, very weak technique. Okay, even the detector is doing a lot of job to get the informations. So if you have an additional barrier like a fluorescence effect, it again suppress the detection process. In order to avoid that, the scientists have predicted that using a higher wavelength like higher region like 785 or 1064 will have a lower energy, and the absorption of the incident light, I mean, this carries a lot of energy, no? So the functional group may not capture the quick energy transfer can be avoided by absorbing the photonic energy. So if you use then the fluorescence can be suppressed, and few parts will be taken care by the software itself. Software also have some provision to get the maximized Raman lines from the material. So that's the main reason we have a 785, especially people who are working in a bio, like bio samples and some natural material like extracts, plant extracts, and the live samples like live cells, like those of the compounds are should be used. I mean, that should be characterized by 785 laser, because that should have a less energy, and you can precisely no, without damaging the surface, you can keep the sample alive. So that kind of features is highly useful. So that's why we have a 785 laser. And filters, of course, the Rayleigh will be there, that is inelastic scattering, we need to eliminate that, and some of the anti-Stokes that may not be highly useful with respect to the structures. And gratings, the role these are the compound within the spectrometer I'm talking about, and the gratings are also to get the good no, light beam from the laser source. And the CC detector, of course, it helps to get the information from the spectra. And this is a additional feature covering from the microscope part. As I told you, microscope is not only for viewing the sample, you will get the image information as well. So you can if you have a sample, if you have a microscope, you can see the surface in a particular length, and if you are interested, you can scan wherever you are interested. Like if you want to know this particular particle, then you can allow the beam here, and this is called point mapping. So this will be pointed. The same thing can be recorded in the form of spectra. So you will get the spectra as well as the image. So if someone asks how sure about this spectra is only from this particle, so the software creates some kind of colors or some artificial or not artificial. Of course, it's a software job that it's making a print on the images. Okay, this kind of mapping will be helpful to confirm that this particular phase is only located here, and you can play accordingly. And you can also do the line mapping. If you have a more number of layer kind of structures, you can draw a line across the layers, and you ensure that where this particular band or this particular compound is located. And you can also do the area mapping. If you have a time, then you can scan the entire area, then you will be able to see these two colors are different. So one can understand, okay, this is this compound. If it is A, then A is only here, or other colors is different. So B is surrounded like that. So the distribution you will be able to clearly understand. So this is a Raman mapping. It's highly helpful for pharma sector. So they have a different composition. Maybe I'll also talk about it later. Okay, and you can also do depth profiling. It's again multiple. I mean, you can keep on shining the laser at some extent. Like you can constantly allow the laser into the sample. It penetrate at some maybe till 10 micrometer we can go, but maybe it's preferred to have less than 5 micrometers. And each layers you will be able to exactly get information. Maybe the first layer from it within few nanometers or within micrometers, you can exactly get that information if you continuously allow the beam penetrate into the layers. That's called depth profiling. So it is highly useful for thin film samples. And we can also do some high temperature measurement, because if you have any ceramics or insulator kind of things, even dielectrics that are highly influenced by the temperature. So how a person can understand if the material undergoes some temperatural influences, so the structural disorders and changes, one can intuitively acquire that information by heating the sample in each temperature. Like you can start from RT, room temperature, to 1000 degrees Celsius. That is highly possible. And what are the key advantages here? So it is again easy identification of structure by the fingerprint bands, and you can cover broad limited applications, and even you can detect a trace amount, and the spectral coverage is wide, so can at a single stretch, this is something very important, you can single stretch, you will get the most of the bands covered from 50 to 4000 or 3500 centimeter inverse, and there is no sample preparation required. And of course it's a completely non-destructive technique, so you can use a sample and very little sample is enough. And of course it's very sensitive, even small changes within the material, and there is no need of solvent or kind of thing, and even you can get that information too. And of course very easy to use, and there is no shape is really required. Of course few have to like very specific about some sample, like the surface should be flat, that's the only criterion. And within this I'll move to the interpretation part. So what are the things we can understand? Like Raman frequency is a major information. So we'll get that number, what frequency the number is giving. From that, you can get the phase or composition. I say composition, it's not a stoichiometry composition. Of course, the what is MOS2, MOO3 is completely different. So these two have a different phase and different wavelength. From that, you can identify from the Raman band, not from one MOS2 that decompositional things cannot be highly possible. And the shift, all the changes within the material, what you process, what you synthesize, it's all will be reflected in the shift. Okay, if person doing A sample and some changes B is producing, so that will be reflected in the shift in the frequency number, whether left or right, based on the numbers. Okay, and the profile, like a polarization, how broad it is, how sharp it is, what is the intensity, what is a deconvoluted effect, like within the spectra you can see a lot of sub peaks, so that all have a different information about the material. And of course the width is direct information about the crystallinity. So there are some software you can use that you can exactly measure the width and with respect to the intensity, that also will give you some idea about the crystallinity. And of course the thickness, the intensity is all about the abundance. So if you say one particular frequency is that number, you can infer that okay, this is the amount it present within the compound. So that kind of information you will infer from the intensity numbers. And what are the advantage or limitation, disadvantage or limitations? It's not an quantitative measurement. You will not able to tell the quantity or composition directly from the technique. It is a purely qualitative. Is it yes or no? The compound is present or no? This functional group is there or not? That kind of things you can easily come to conclusion, but you will not be able to say the compositional calculations and all. And it is not preferred or not advisable for doing metallic substance, pure metals and alloys, unless they have a surface oxidized species. If you have a no stainless steel or some titanium plates, it's a pure metal, but still the surface oxides will be there, then you will get some peaks. But highly pure metal, they have a highly electron clouds, that's not a pure no kind of a covalent structure. So and another problem, you will not be able to get the focused light. It's the photon will get reflected. So reflection is the problem in doing Raman for metals. And it is highly sensitive, like environment need to be taken care, like light and atmosphere, humidity, everything need to be optimized to get a good quality spectrum. And of course fluorescence is a big very big challenge. So mostly the organics with the functionalities have a fluorescent effect, so one have to carefully select the suitable laser and the parameters to get the good spectrum. And of course it's sensitive. And within this, I'll go to the specific applications, and I'll take a few typical example or most widely useful for doing Raman, kind of metal oxide and especially carbon-based materials and few polymers and biomolecules and medicines. So as I told you, most of the metal oxides are easily predictable by Raman. You will get the band around 460 to 78, 750, and some of the secondary yellow bands can be up to 1800 or 900. So these things can be easily predicted. In addition, with the support of XRD. If you have XRD, then you can get some additional information about the phase and crystallinity from Raman 2. And so all the the stretching things which may not be available with XRD, but here you can get the the difference in the shift that will tell you about the different modes can be possible within the compound. And of course, as I told you, the crystallinity, if you calculate the full with half maxima of the peak, that will give you some idea about the crystallinity and phase kind of information. Of course, this the vacancies, because the light are very sensitive to with the defects or the impurities, so that will also involve the scattering, so one can easily come to know what are the defects within the material. So that kind of metal I highly prefer to do Raman. So defects analysis are highly possible. And scenario here. So you see the numbers. See, this is not simple number. It's a fingerprint or the characteristic wave number of a particular bonding. So if you observe a number from Raman, you can come to know, okay, this kind of bonding is there within the material. So we do not do anything. So it's already predicted even years before, and the people have assigned all the possible stretching one molecule, what kind of process it can undergo by the influence of doping and all things. So they have assigned a different point groups and with respect to the wave number. So if you have a data, you can simply compare the numbers and do the further analysis. And moving to the organics, so of course it's it's have a very good functionality to scatter the electromagnetic radiation, and one can easily predict whether it is OH or NH or CC or CH kind of thing. So that prediction can be done. So this is a typical example of a sugar molecule. So sugar have a unique bonding with the glycyl bond like CO and alcoholic functionality. All are the primary alcohol that have a fingerprint appearance in the range of 1300 to 200. So you will be able to say, as this is a polysaccharide, this is a simple sugar. Like that, you can know, and you can easily identify whether it is salt or sugar within minute. So that's a great advantage of Raman. And the same way, some of the key Raman shift values or the frequency number which tell you about the structure. So the piece of information, piece of bonding, you can have an idea what the compound it is. Okay, because functional group is a key. Other structure, other skeleton will be the same, but the functional group are more reactive or sensitive to the molecule. So you can exactly tell about that information. And of course, the Raman is highly popular or they are widely used for characterizing the carbonaceous material like graphite and graphene, GO, RGO, and their family of material. So because the amorphous, because the most of the layers kind of structure is not easily if you do XRD or other techniques is not possible, but Raman you will get because it's a defective structure, graphene and graphite, because graphite have a bundle of a graphene shade. You are just literally taking out few layers out of it. So it has coming with a lot of defects and structural disorders. So that's all sensitive with the photonic scattering. So that will easily you can predict from the well-known DG band. As you see, the shift values are X and the intensity is there. So you see graphite, as the graphite is bundled, there is no defects in the or less number of defects here. So this G denotes for graphitic nature. It's highly graphitic nature. That means lot of layers of carbon, hexagonal carbons within the structure. But if you peel off or taken out some layers like graphene or graphene oxide by synthesis, So it end up with a lot of defects because you are ultimately scratching few surfaces. So that defects, you can see the intensity here. So there is a very less number of intensity, but the D stands for defects. So you can see the defect band. So that you can tell it is not pure graphene. It is maybe a graphene or graphite oxide. So the ID, I mean, intensity of a D band and intensity of the G band, the ratio will tell you what is the quality of your GO or RGO, or if it is a graphite. So this is a easy prediction of graphene. Even the graphene, how pure it is, how oxidative functional groups are present in that. So the ID by IG ratio is a simplest and precise method to predict the carbon family members. Okay, so this way, I mean, this is highly helpful. Even the characterizing the nanotubes, like how thick it is, how the wall thickness, and how many tubes are within the group. So these are all highly can be differentiated if you apply a good quality laser, because the spatial resolution should be very low. Maybe that way you will be able to tell the number of layers in the or tubes in the compound. And of course, what I'm saying is the different structural changes happens with the tubes, and you see the spectrum. So like what are how the Raman can help you in differentiating the multi-wall carbon nanotube and the single wall carbon nanotube. It's all related to the bandwidth and the intensity. So it is directly relating, and you can do all the secondary level analysis by taking the numbers, not by simply looking at the shape. So you do the calculation, and you will be able to tell. And okay, fine. So these are the example, like characterizing a polymeric compounds. Polymers, fine. These are highly, very close member of Raman. So you can easily get some information about characterizing the polymeric compounds. So again, with respect to the fingerprint identification of the functional groups. Say, for example, the PET bottles are it's not completely made up of single polymer. You have a combination of other polymers. So one can do Raman, but different portions. Then you plot that full width half maxima of a particular group. So this is a PET, polyethylene terephthalate group, is responsible for that polymer. So in that value will tell you the crystallinity, which portion is highly crystalline, because as I told you, the full width half maxima is mainly related to the ordered, I mean, crystalline structure of the material. So that way, if you get that number, you will assume that which portion of your bottle is highly made up of polyethylene terephthalate, or some other compounds are the weak degradation of the structure or poor in the crystallinity within the bottle. So this kind of analysis or possibilities are there with the Raman. And the pharma, of course, as I told you, the mapping part is highly useful for their applications, because they mix with a lot of organic substances with a different ratio. It's a very precise compositional materials. So if you do one mapping, so it's a complete fast scanning or surface scanning. So you see three different components, like aspirin, paracetamol, and other components are surfacely coated. So you see the distribution. So one can exactly recalculate, or they can check whether their formulation is exactly present in the tablet or not. So as I said, the paracetamol it should be distributed in that pattern is confirmed here. So all the surfaces scanned with respect to the spectrum. So wherever you see the black, I mean red spot, is presence of paracetamol, because the amide is a functionality here. So you can get the peak around 1650 or 750 range. So that is a key information in confirming the distribution of the different pharma component within the tablet. So in that way, it is highly useful. And identifying the marine species or minerals, it's fine. These are highly useful. Like if you have a pearl, like pearl is mineral, of course, it is very expensive. Pure substance have a band, like it's a pure calcium carbonate. But if you have a synthetic polymer, I mean synthetic pearl also available in the market, one can buy within 10 rupees or paying 50 rupees. But PL, original PL will cost around 2,500 or even more, I don't know. But this key difference one can easily identify by doing Raman. If you get a calcium carbonate peak with a less crystallinity, so you can know, you come to know this somewhat original. But If it is a synthetic or a flux kind of things, then you will get all the polymeric bands for the appearance. So this kind of analysis is highly useful. And of course, differentiating the seashells, I mean the marine species, also it's all made up of oxides and some the mineral substances. That also can be easily differentiated. So which component is made up of which kind of substance. And of course, it's also useful for the medicinal application, tissue analysis, what kind of protein is distributed. If people are doing some calcification process, incorporation of some, I mean, it's a calcium-rich substances. If you have, then you will be able to tell whether the calcium are incorporated within the tissue or bone or something like that. So that way, it is highly useful. And the protein analysis also can be easily done, because it's if you use 785 laser, you will get very good spectral data. And these are the work, very specific examples what we are doing in the microplastics to identify the microplastics from ocean source. So you can see the microplastic extract from the ocean. So we have a NCCR, I mean NCCR consultancy, we are supporting research. They are doing Raman with us. So for their sample, it's you cannot do simply by other technique like microscope techniques, and the polymeric distribution, what kind of polymer it is. So their degradation studies, everything can be possible once you know the kind of polymer within the plastics. So that way, the Raman is helpful. So you can see the optical images of a very tiny substance, and the focus should be there. And if you focus on particular area, and even you can do the mapping here, like if it is polyethylene, it can be a polybutylene. So that kind of differentiation can be done if you do a Raman. So that polymeric compositions present in the microplastics are highly helpful to the environmental application like microplastics. And of course, this high temperature data, what we having like cerium oxide, it's a highly doped structure, heavy, so highly influenced by the high temperature, like more than 300 to 400 degrees Celsius. So you can see the formation of vacancies. So because it's a allovalent doping, so it end up with a lot of oxygen vacancies that all are sensitive to the photonic scattering. So, and the distribution of their I mean, throughout the microstructure, with which grain or which boundary the vacancies are sensitive, you can map accordingly. So these are the technique are highly useful to understand the behavior of the sample. And of course, a few works of my colleague, so they're working on the diffusion studies. They have a multiple layer, as you see, it's a substrate, that is an alloy substrate. They have a 3 different gradient coating like nickel oxide YZ combination. So their intention is to know the nickel oxide distribution throughout the layers. So how do you know? So we have did the depth profiling, and so we have mapped the surface. You see the red. So the intensity is only with respect to 558 nanometer. It's from nickel oxide, cubic nickel oxide phase. So that intensity number varies from layer to layer. So one can see the surface, I mean the bottom of the substrate have, but the middle layer of the layer have a deviation in the intensity. I mean the presence of nickel oxide is not uniform. Of course, it is uniform at some extent, but the distribution cannot be expected throughout the structure. So you can see some black or dull intensity here. So similar to that. So that means the distribution is not very even, but of course it's diffused completely entire layers. So that's useful for vitrification of nuclear waste. So that person can go ahead with like, okay, nickel oxide is helpful, or it is present with some extent of distribution within the layer. So that is I mean this work we have done through Raman. And of course, as I told you, so these technique is one technique is it cover a variety of materials with a variety of domain. So you can do most of the material you can cover and get the basic idea what substance actually it is. So it's highly helpful for understanding the structural effects. And within this, I summarize. So the technique is very powerful, or very useful technique for characterizing a material. It is a fingerprint technique, of course. It's useful for characterizing the interaction of the photon and the molecular vibrations, because the vibration is the key factor for getting the spectrum. And the quantification may be possible in a relative manner from the intensity values, and variation, small changes can be easily absorbed, and the mapping is highly useful for if you have a heterostructures or more than one layer or more than one compound within the powder. So that can be easily differentiated if you do mapping. And the profiles need to be not, it's not alone, of course, it's only raw data. So all the post processing need to be done to get more data, so with the help of software and all, and a proper understanding of the materials. And for a simple interpretation, you can use some online database. You can correlate the spectral number with the profile with the structures. Okay. And of course, these are all the specification what we have with our system, and what the laser we have, what are the resolutions, and the microscope have what are the capabilities, and high temperature mode and all. And you are all welcome to use, or you can have all the access. I mean, you can